In this video, we're going to go through some proof by contradiction examples. First of all, have a little think about the proofs that you learned in Unit 1. Can you remember the names of any of them?
So here are the three types of proof that you've learned already in Unit 1. The first one we looked at was called proof by deduction. So this is one where you just use facts that you already know to prove other facts. We then moved on to proof by exhaustion, which is one where you try all the possibilities and prove that something always works. And then the third type of proof that we looked at was called disproof by counterexample. So this is one where you prove that a statement is false by finding one example that contradicts the statement. So they are the three types of proofs that you've learned already. And the one that we're going to learn today is a different type of proof, and it's called proof by contradiction. Now, I recommend that for any proof by contradiction question, you try to follow this structure. So there are sort of three main steps to proving something by contradiction. So think about, first of all, what the word contradiction means. If you contradict someone, you disagree with them. You have a different opinion. So with the proof by contradiction, what we do is we're trying to prove that a statement is true. So first of all, we assume that the opposite is true. Then we show that the opposite, being true, is complete nonsense. And then finally, we say that if the opposite is complete nonsense, then the original statement must in fact be true. So that's the idea, those three steps. Step 1, assume that the opposite is true. Then show that this is complete and utter nonsense. And then just say at the end that because the opposite is nonsense, the original statement therefore must have been true. Now, there are lots of different types of questions that they could ask you in an exam on this topic, but as long as you follow those three steps, you should be okay. There are a couple of types of questions, though, that seem quite popular with the examiners. So I'm going to go through with you now 4 different types of example. There are more than that in the booklet, so I recommend you have a look at the examples in the booklet as well. I think there are about 7 in the booklet. But I'm just going to do 4 now that I think will help you to understand the vast majority of the questions. So this first example says, prove that if n squared is even, then n is also even. So if you just think about some square numbers, so let's think about a square number, for example, 36. 6 squared is 36, which is even. And 6 is also even. If you think about any even square numbers, 36 was just one of them. What about 100? That's another one. 100 is 10 squared. 100 is even. 10 is also even. So you can see that this statement seems to be true, but I've only chosen there 2 random examples that it worked for. We've got to prove that it would work for any value of n. So we're going to do that by proof by contradiction. Now this one comes in handy later on because there's an example later on that we're going to actually use this fact in. Some little hints before we start. This question is talking about even and odd numbers. So remember from Unit 1, if something is even, then it can be written as 2k, because if you multiply anything by 2, then you get an even number. So an even number could be written as 2k. You don't have to use k, it's just a commonly used letter. And then in a similar way, any odd numbers could be written as 2k plus 1, because if you take any number k and you multiply it by 2, you get an even number. And when you add 1 to that, it always becomes an odd number. So 2k plus 1 is one way of writing an odd number. Of course, you could also use 2k minus 1, but I'm going to use 2k plus 1 here. These would only work, however, if k was an integer. Okay, so let's get started then on the proof. We're trying to prove that if n squared is even, then n must also be even. So step 1, assume that the opposite is true. We'll assume that if n squared is even, then n must be odd. So you can see that the bit I've underlined, n is even, we're assuming the opposite, n is odd. And we're now going to try and show that that is nonsense. Well, if n is an odd number, then that means that it can be written as 2k plus 1, where k is any integer. Now in the statement it said that n squared was even, so let's now work out what n squared would be. So we're saying that n is 2k plus 1, so n squared would be 2k plus 1 squared. Which if we square out that bracket using FOIL, we get 4k squared plus 4k plus 1. Now remember from the question, n squared is even. But hopefully by looking at this, you can spot that that isn't the case. This is actually an odd number. If you want to try and show that something is odd, try to write it as 2 times something plus 1. Well, this can be written as 2 times 2k squared add 2k plus 1. So you can see that I've just factorised that first part. I've taken out a factor of 2 so that I can write this as 2 times something plus 1. So I've proved here that n squared is odd. But in the statement we were told that n squared is even. So what we've shown is that the opposite statement is nonsense. So let's just quickly recap that. We assumed that n was odd. We then worked out what n squared was, and it turned out to be odd. But that's nonsense because we know that n squared is even. So we've shown that the opposite is nonsense. So finally then, as in all proof questions, you write a little conclusion. So something along these lines. Say that n is odd is not true. So there's a contradiction. Therefore, the first statement must be correct and n must be even. So here's another example that says, prove by contradiction that for all real values of x, x squared add x is greater than or equal to 7x minus 9. Now this is a very common type of exam question, one where you've got a squared and you've got an inequality. And there's quite a nice little trick for these sorts of questions to make them quite easy to prove by contradiction. So the hint at the top, with this one, the trick is use completing the square and end up with a square which is negative, which is obviously nonsense because you can't have a negative square number. So that's the hint for this question. So let's get started. We're trying to prove that x squared add x is always greater than or equal to 7x minus 9, no matter what x is. Step 1, assume that the opposite is true. Instead of assuming that x squared add x is greater than or equal to 7x minus 9, we're going to assume that x squared add x is less than 7x minus 9, because less than is obviously the opposite of greater than or equal to. So the first thing I would do with this one is to get everything over to one side. So if I write x squared, I'm going to take 7x off both sides, so that's minus 6x. I'm going to add 9 to both sides, just to make the right hand side 0. So that's something that hopefully you're used to doing with quadratics, always get everything onto one side. And then the left hand side can be factorised. Now when I factorise this one, I get x minus 3 and x minus 3 again is less than 0. So in other words, I've got x minus 3 squared is less than 0. So now I've shown that something squared is less than 0. So I've shown here that a square number is negative. Now obviously this is not true because a perfect square is never negative. When you square anything, it's always 0 or higher. So we've just shown that the opposite is nonsense. Remember, this was the statement that was our opposite to the original one. And we've shown that it's complete and utter nonsense. You can't have a square number less than 0. This is nonsense. So we finished our proof and we just need to write now our little conclusion at the end. So something along these lines. X minus 3 squared is less than 0 is not true. So there is a contradiction. Always make sure you say that word. There is a contradiction. So therefore the first statement must be correct. So we've proved that x squared plus x must be greater than or equal to 7x minus 9. So as I said, that's quite a common exam question, and it's quite a straightforward one. If you can remember the little trick, complete the square and end up with a square which is negative, and that's your contradiction. So here's another example. I've taken this one actually from your booklet, and it's fairly similar to the one we've just done. Prove by contradiction that if x is real and x is greater than 0, then x add 4 over x is greater than or equal to 4. Now, even though it doesn't look much like the last example, because the last example was a quadratic, we can actually use exactly the same method because we can turn this one into a quadratic. The obvious problem to start with, or the obvious part that's not very nice, is that fraction there. So to get rid of the fact that there's a fraction in the question, we could multiply everything through by x. And if you multiplied everything by x, not only would that get rid of the fraction, but it would also create an x squared. So you can see then that it would be a quadratic, and it would be very similar to our previous example. So let's have a look through the proof. So step number 1 is to assume that the opposite is true. So instead of x add 4 over x being greater than or equal to 4, we're going to say that x add 4 over x is less than 4. So you can see there that the inequality has been swapped around. So we've assumed that the opposite is true. Now we're going to try and show that that is nonsense. So as I said earlier, if we multiply everything through by x, that's going to get rid of that fraction. And the x at the beginning is going to become an x squared. The 4 over x will become just 4, and the 4 on the right hand side will become 4x. So we've got our quadratic. Then we can get everything over to one side by subtracting the 4x. So we get x squared minus 4x add 4 is less than 0. And then we factorise or complete the square. This one, when you complete the square or factorise it, you end up with x minus 2 squared is less than 0. Now obviously x minus 2 squared can't be less than 0 because when you square anything, no matter what it is, it's never less than 0. So this is nonsense. So we can write our conclusion that because the opposite statement was nonsense, then the original statement must have been true. So therefore x plus 4 over x is greater than or equal to 4. So this is the last example that I'm going to go through with you. Even though it's still proof by contradiction, it's a totally different type of question to the ones we've looked at so far. They could apply proof by contradiction to any context, but this is another one that's quite common. I've seen it in quite a few exam questions where you're asked to prove that something is irrational. So on this one we've got root 2, which we know is an irrational number, but up until now you've always just been told root 2 is irrational. And for example, pi is irrational. You've been told these things in the past, but now we're going to actually prove it. So for this one, it's useful to remember the difference between a rational and irrational number. So the hint at the top is just to recap what a rational number is. It's any number that can be written as a fraction. So for example, a over b. You can use any letters. I've just chosen a and b. So a rational number could be written in a fraction in that way. But the question says, prove by contradiction that root 2 is irrational. So the first step would be, assume that the opposite is true. So we are going to assume that root 2 is rational. Well, if root 2 is rational, that means that it can be written as a fraction. So root 2 could be written as a over b, this is our fraction. And let's assume that this fraction has been simplified into its lowest terms, into its simplest form. So if it's been cancelled right down, then a and b are not going to have any common factors, apart from obviously 1. Now that's really important for this question. We're assuming that this fraction has been cancelled right down, so that a and b have no common factors, apart from obviously 1. Now we're just going to rearrange this statement to make it look a little bit nicer. So we started off with root 2 equals a over b. Well, to get rid of the fact that there's a fraction, we could multiply both sides by b. So if we multiply both sides by b, we'll have root 2 times b on the left and then a on the right. Next, we can try and get rid of the root sign, because that's not looking very nice. So to get rid of the root sign, we could square everything. So to get this next line, I've just squared all of the left-hand side and I've squared all of the right-hand side. So when you square root 2, it becomes 2. And then obviously if you square b, it becomes b squared. And if you square a, it becomes a squared. So now we've got this statement. So this statement tells us that a squared is equal to 2b squared. So a squared is 2 times something. It's even. If it's even, that means that it's got a factor of 2. A squared has got a factor of 2 because it's even. Well, remember from one of our previous examples, anything that's even can be written as 2k, where k is any integer. So if we know for a fact that a squared is even, then a is also even. That's something we proved earlier on. And if a is an even number, then a can be written as 2k. So in my statement, instead of having a now, I'm going to change it into 2k. Next, I'm going to expand that bracket on the right-hand side so that 2b squared is equal to 4k squared. And now I can see that I can half both sides to simplify a little bit. So if I half both sides, I've got b squared is equal to 2k squared. So now I can see that b squared is even because b squared is 2 times something. So b squared has a factor of 2, it's even. And from earlier, the proof that we did earlier on, if b squared is even, then b is also even. Right, this is the point now where we've got our contradiction. Earlier on, we said that a and b were integers with no common factor. But we've just proved that a is even and b is also even. Well, if a and b are both even numbers, then they've both got a common factor of 2. And this is a contradiction because we said that they would have no common factors, and they have actually both got a common factor of 2 because they're both even. So we've got our contradiction. So our assumption must have been nonsense. So therefore the original statement must have been true. So we've shown that the opposite statement is nonsense. So we can write our conclusion, something along these lines. A and B both have a common factor of 2. This is a contradiction. So therefore the first statement must have been correct. So root 2 is in fact irrational.